Modern applications often include many features, and as these systems grow, managing everything in one large application becomes difficult. This is where microservice architectures become useful, as it breaks down an application into small independent services, each responsible for a specific function. Imagine a growing web application as a single monolithic code base. At first, everything works fine, everything lives together. User accounts, payments, notifications, search, analytics. But as the app grows, deployments become risky. A small change in the payment module can accidentally break notifications. Scaling is inefficient. To handle more traffic on the search feature, you have to scale the entire app. Teams face bottlenecks. Developers step on each other's changes, slowing down the process. And this is where microservices comes in. Instead of one giant application, we split it into small independent services, each responsible for a single domain or business capability. Example, if there is a user service, that service only manages user account and authentication. If there is a payment service, it processes payments and transactions. If there is a notification service, it sends emails, SMS, and push notifications. Each service has its own database, its own deployment cycle, and its own scaling rules. Microservices turn a tightly coupled monolith into a flexible modular system that can scale, evolve, and recover from failure more easily. In a dynamic environment, services start, stop, or move across servers or containers. Static addresses don't work anymore. How can one service find another? Service discovery solves this problem. It's like a live map of all available services and their locations. There are two main approaches. First is client-side discovery. The client queries the service registry to find available service instance, then picks one to call. Server-side discovery. The client sends requests to a load balancer or API gateway, which routes the request to the correct service instance automatically. Example, the user service wants to call the payment service. Instead of knowing which server is running payment, it asks the registry who's available, and it communicates directly client-side or goes through a gateway, which is the server-side. Now, why does it matter? Without service discovery, microservices would become unmanageable, especially in systems with hundreds of services running in cloud environments. In a microservice ecosystem, you may have dozens or hundreds of services, each with its own endpoint. Asking clients to talk to each service directly is chaotic. The solution? API Gateway. A single entry point for all client requests. Some responsibility of an API gateway are to route requests to appropriate services, handle authentication and authorization, apply rate limiting and caching, and aggregate responses from multiple services into one. An example can be that Netflix uses API Gateway to allow their mobile applications to communicate with multiple backend services seamlessly. A single call to the gateway may fetch user info, recommendations, and watch history all in one response. API gateways simplify client interactions, enforce security, and reduce coupling between client and services. Microservices don't exist in isolation. They need to talk to each other. Any method of communication affects performance, reliability, and scalability. Two main communication patterns are: first is synchronous communication, which is request or response based. One service calls another and waits for a response. An example can be that the user service asks the payment service to process a method and waits for a confirmation. It is simple and easy to understand, but it creates tight coupling, so if one service is slow or down, it can block others. Another is asynchronous communication, which is event-driven. Software publishes events and other services subscribe to them. Payment service publishes a payment completed event, and notification service subscribes and sends a confirmation email. It decouples services, improves resilience, and handles high traffic better, but its con is that it is more complex to implement and debug. Eventual consistency becomes a factor. Choosing between synchronous and asynchronous communication is a trade-off between simplicity, reliability, and scalability. Each microservice ideally has its own database to avoid shared state bottlenecks. Why not share a database? Tight coupling leads to schema conflicts, and scaling one service can affect others. Services own their own API and expose it through API or events. An example can be user service stores authentication info while payment service stores transactions. Payment service never directly queries the user database, it interacts through APIs or events. This promotes encapsulation, autonomy, and scalability. Microservices offer flexibility, but they also bring challenges. Network complexity. Servers communicate over the network, introducing latency and potential failures. Monitoring and observability. With dozens of services, tracking errors requires centralized logging and monitoring. Consistency. Data may be eventually consistent rather than immediately consistent, resulting in especially in asynchronous systems. Good design balances independence, reliability, and performance. Now, bringing it all together, microservices and SOA allow systems to scale independently, deploy updates without affecting unrelated services, and isolate failures, improving reliability. Some key components to remember are service discovery, which is finding the right service dynamically, API gateways, which simplify client communication and enforce policies, and communication patterns, which decide between synchronous and asynchronous. This architecture forms the backbone of modern distributed systems, powering everything from e-commerce platforms to video streaming services. In the next video, we'll combine with performance optimization, caching, and edge techniques to make microservices fast and responsive. Thank you, and I'll see you in the next one.